Hi guys, welcome to the first lesson of our very last unit of the year. This is a unit about differential equations, and we are going to start by defining what a differential equation is. A differential equation is an equation that contains a function, and one or more of its derivatives. The solution to a differential equation is going to be a function. So we want to contrast that. This is a solution to a differential equation. It's a function. We want to contrast that to the solution to an algebraic equation, which is a number, right? We know that when we say x plus 3 is equal to 7, when we solve that, x is a number. But a differential equation is going to be something like dy dx is equal to 2, for example. So the answer to this problem is going to be y, the function y, is equal to 2x. That could be one answer to the problem. But you know that it could also be 2x plus 5 or 2x minus 3, right? In fact, the general solution to that is any function 2x plus c. So you've already seen simple differential equations like that. So what we're taking away, though, is that the answer to this differential equation is not a number, but it is a function. Okay, so now differential equations can be made up of the first derivative and also higher order derivatives. And so the order of a differential equation is going to mean the highest derivative that is in the equation. Okay, so this is our order of a differential equation. So for example, a differential equation which said d cubed y dx cubed plus d squared y dx squared plus y is equal to x. This is a third order differential equation because the highest derivative we see here is the third derivative. So differential equations are used a lot in science and especially in physics, for example. You might be familiar with some of them, like, for example, the equation that governs how a spring moves is going to be an equation that looks like d squared x dt squared is equal to minus kx. That would be spring equation in physics. Or we have what we call the natural growth equation, which is dy dt is equal to ky. This is a very famous equation, and we're going to spend a lot of time learning about that. Okay, so to understand differential equations, we need to be comfortable with the concept of variation. So you know from Algebra 2 that there are three types of variation. Direct variation, where we say y, the variable y, is directly proportional to x. Inverse variation, where y is inversely proportional to x, y is equal to k divided by x. And then maybe a joint variation, where y is directly proportional to x and z. And I guess there's also combined variation. Y is directly proportional to x and inversely proportional to z. So these are some of the things you've seen before. And differential equations are going to often involve this idea of variation. So let's see how we can model some relationships between variables to write differential equations. So the first example here has various differential equations expressed in words, and we have to translate them to an equation. So here we begin with the rate of change of h with respect to t is proportional to the square root of h. So we literally want to pick this apart and translate the words into math. So we know rate of change is a derivative, and this with respect to t means that this whole statement here becomes dh dt. The rate of change of h with respect to t is, in math, is usually an equal sign, and proportional is going to give us our proportionality constant K. And here, be careful, the square root of H means the square root of H. So don't write H squared, it's the square root of H. So there's a differential equation. Let's do another one. Pause the video and see if you can do it, and then check out the answer. The rate of change of m with respect to t, so dm dt, is equal sign inversely proportional. So I know I'm going to have my k on top, and then I'm going to have something on the bottom, the cube of m. So I'm going to put m cubed on the bottom. So dm dt is equal to k over m cubed. That's another differential equation. The rate of spread of a disease is proportional to the number of people n who already have the disease. So the rate of spread would mean dn dt. How fast is the number increasing, the number of people who have it? This we're saying is proportional, so is proportional to the number of people who have the disease. So that's just n again. So dn dt is equal to kn. This is an example of that natural growth equation that I referred to earlier. Okay, this next one, we need to add some words here that I forgot. It's about a rumor spreading at Cathedral, and we want to add that CCHS has 1,600 students. We need that information in the question. Okay, I just forgot to type it in. Okay, so read this. Rumor is spreading among the CCHS school community at a rate proportional to the product of the number of students n who have heard the rumor and the number of students who have not heard the rumor. So first thing to realize is if n students have heard the rumor, then 1,600 minus n will be the number who have not heard the rumor. So we need to be able to realize that. And then we can write our differential equation. The rate of spread means how fast is n growing, right? The number who have heard it. So dn dt is equal to the proportionality constant, and then the product of n times 1,600 minus n. And when they give us this initial condition, this is something that we're going to need to solve some differential equations or to get a particular solution. You've already kind of seen this, right? Where we just said above that if dy dx is equal to 2, there's a differential equation. We know y can be 2x plus c. But if I tell you that y of 1 is equal to 1, then you can go in here and put in the numbers and solve for c and get a particular solution, right? So this would be the general solution, and this would be the particular solution. We've come across this before. So sometimes a differential equation will have an initial condition like this, and that is in order to help us when we solve it to solve for the constants. So the way we would write that here is n of 0, the number of students who have heard the rumor, at time 0 is equal to 2. And that would be our answer. This right here, all of this, I should say, is that answer. Okay, this next one, the rate of change of the volume of a balloon that is being blown up is proportional to the square of the radius. So you want to give some names to things. So volume of the balloon is V, the radius might be R. So the rate of change of the volume is dV dt. And we know that that is proportional to the square of the radius. Okay, then we have Newton's law of cooling. This is another very famous differential equation. Says that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings. Suppose you just poured a cup of freshly brewed coffee with a temperature of 95 degrees in a room where the temperature is 20 degrees. What is the initial condition? Okay, so let's take this apart. We've got a law that says that the rate of cooling, so that means it's the rate of change of the temperature, in this case of your cup of coffee, right? So your cup of coffee is going to change its temperature at the rate d big T dt, if T is the temperature of coffee. Then d big T d little t, this T is temperature, this T is time, right? is going to be equal to or proportional, put my K in, the temperature difference between the object and its surroundings. So the surroundings in this case are the room, and the room is at 95 degrees. No, sorry, no, the room is at 20. Yeah, that would be bad. If the room was at 95 degrees, it'd be really hot. The room is at 20 degrees. The coffee is initially at 95 degrees. So the initial condition is there that the big T, temperature of the coffee at time 0 is 95. This would be my initial condition, and the equation would be d big T dt is K times the difference between the temperature of the coffee and the room temperature, right? That's coming from these words here, the temperature difference between the object and its surroundings. So the object temperature goes first and then the surroundings next. So this would be part of the answer, and then you'd have to say the initial condition T of 0 is equal to 95. So this whole thing would be our answer. Okay, so as we just said a minute ago, differential equations have a general solution and a particular solution. So for example, if my differential equation is dy dx is equal to x squared, we already know that we can solve this by taking an integral or an antiderivative, and we're going to find that y is equal to x cubed over 3 plus c. Okay, so that would be my general solution. And if I told you that this y that you're solving for has to go through the point, for example, 0, 1, then you would say, okay, I will now put in 1 is equal to 0 plus c, 0 cubed over 3, which is 0 plus c. So c is equal to 1, and so now I could write a particular solution for that same differential equation. Y is equal to x cubed over 3 plus 1, right? What does all this mean? This means that this equation, right, has a whole family of curves that look something like this, right? X cubed over 3 plus c would be any of these curves, and there'd be an infinite family of those. There's lots more curves that I'm not drawing that are in here and in here, and there are just a whole infinite family of curves with that shape, and all of them would have a derivative that has a shape of x squared. All of these curves would have the same blue derivative, okay? But if I now specify that I want a curve that goes through this point, then I have said, okay, I want the curve that goes right through 0, 1, for example. And so then I'm pinning it down to this curve, and that would be then the particular solution that we found here. So that's the idea. Now, you have already done lots of differential equations without really knowing that that's what you're doing, because when you find an antiderivative or you do an integral, you are basically doing a differential equation solution. So here, let's just review some of the types that we have done before. If it says solve dy dx is equal to this, then we are just going to take the integral to find y. So y is going to be the integral of all of this, the antiderivative, right? Because we know that if, you know, the dy dx that we're given is sitting here, that's my y prime, this is y prime, then I take an integral to go back up to y, and that's all we're doing. We're just solving for y. So y then is equal to x squared over 2 plus, minus 2x cubed plus ln x plus c. Okay, so pause the video and see if you can do all of these. These are all review from the past, just finding antiderivatives or integrating. That's what we're doing here. Okay, so here again, we are integrating. Y is the integral of 5 to the x ln 5 plus 1 over x squared plus 1 all dx. And so remember that the antiderivative of this is just 5 to the x, and the antiderivative of this is just tangent, arctangent x. So I have a plus or minus here inside the integral, so I can do this in pieces, and I just throw on my plus c and I'm done. This next one looks like a u sub. Notice we're saying y prime is equal to this. Or, the other two said dy dx. You got to be comfortable with both notations. Y now is the antiderivative or the integral of that, right? I just flipped the order of the product. And then I could say u is equal to 2x cubed, and do this with the u substitution. Du dx is equal to 6x squared. And so if I go back into my integral now, I'll write it in blue. Y would be equal to the integral of rad u, and then x squared, and the dx becomes du over 6x squared. These guys are going to cancel. And so then I have 1/6 integral of rad u du. This is going to be like u to the 1/2, so add 1 and it becomes 3/2, and then flip that to 2/3, so 1/6 times 2/3, and u to the 3/2 plus c, so final answer 1/9 u, which was this, it was 5 plus 2x cubed. Let me just write that more carefully. 5 plus 2x cubed all to the 3/2 plus c, right? So another general solution. Next one is reminding us of particular solutions, right? So we're going to solve this, and then we're going to use this initial condition. So when we're given an initial condition, the vocab that goes with that in differential equations, it's called an initial value problem, right? So when we are given this initial value, it's really because what are we saying? We're saying that y of 0 is equal to 2, right? Or f of 0 is equal to 2. Here's the x, here's the y. So that's why it's called an initial condition, or a boundary condition, sometimes it's called. Okay, it's just that initial condition that we use to find the c. So here y is going to be the integral of 3 sine x dx. So that is negative 3 cosine x plus c, and then throw the initial condition in there to get 2 is equal to negative 3 plus c. And what does that leave me with? C is equal to 5. So final answer here, y is equal to negative 3 cosine x plus 5. And there now you see you have a particular solution to that differential equation. Okay, then let's see. Keep pausing the video and doing these problems on your own, because all of this is just a quick review. SVAG, right? We have acceleration, and then velocity, and then position, right? So recognize that these are all differential equations. When we say ds dt is equal to v, or dv dt is equal to a, right? Those are going to be differential equations. So here, a here, right, is dv dt. And then that is equal to 4 secant t tangent t plus e to the t plus 6t. So then v, we know we're just going to integrate all of this stuff. I'll rewrite it here and integrate. And we're going to get 4 secant t plus e to the t plus 3t squared plus c. Then we're going to put our initial condition in. Velocity is 5 when time is 0. So 5 is equal to secant of 0 is 1 plus e to the 0 is 1. 3t squared is 0 plus c. So I get that c is equal to 0. And I can come back here to just write my final answer. V is equal to 4 secant t plus e to the t plus 3t squared plus 0. So I don't have to write anything. This would be my answer right there, right? And you can differentiate it and see that you would get this thing that we started with. It would solve this differential equation, because dv dt would be 4 secant tangent plus e to the t plus 6t, right? And also, if you put t equals 0 in here, then v would come out to be, let's see, v of 0 comes out to be 4 plus 1, 5, right? So we've solved all that we needed to solve. Okay, so these examples here, example 4a and b, are just a review of the net change theorem. So when we say f prime of x is equal to e to the negative x squared, f of 7 is 3, and we want f of negative 2, then we're just going to use the net change theorem. This is going to be our a value and our b value. The net change theorem says that f of b is equal to f of a plus the integral from a to b of f prime of x. That's our net change theorem. And we're just recognizing that this right here really is a differential equation, because it's really like saying dy dx is equal to e to the negative x squared. And then this right here is an initial condition. And in this kind of setup, we're not finding all of f, we're just finding one point on f, which is f of negative 2. So just to review now, we would just do f of negative 2 is f of 7 plus the integral from 7 to negative 2 of f prime. And we don't care that we're going from 7 here to negative 2 here. We still have a plus sign over here. We still put 7 on the bottom and negative 2 on the top. And you do this in your calculator and you get an answer of 1.2316. And the next one is exactly the same type of problem. You can pause the video and practice that. And this one, we are finding f again, and or y. We are given the f prime or dy dx and 1 point on the graph of f. So again, by the net change theorem, f of 3, this is now my b value, is equal to f of a, which is 7, plus the integral from 1, that's a, to 3, that's b, and then I just plop my f prime in here. This is one that we could do using u substitution, but we won't take the time right now. This comes out with math 9 to be 7.1096. Okay, our examples here, example 5, there's a few of them, is about how do we verify that a solution really does solve a differential equation. And it's just like with numbers. If I tell you, if you're solving the equation x plus 5 equals 7, and I say verify that x equals 1 is a solution, x equals 2 is a solution, you would say, well, yeah, 2 plus 5 equals 7, right? 7 equals 7. You get an identity, so it's a solution. If I asked you to check if another number is a solution, like 1, which I just wrote by mistake, you would go 1 plus 5, is it equal to 7? And you would get 6 is equal to 7, which is not an identity, it's a contradiction. And so we do not have a solution. So it's the same thing here, except we're working with a function. So if we're identifying in the first example the differential equation for which this is a solution, let's take a look at the differential equations. This is actually a very easy problem because all we have to do, the differential equations are just dy dx. So the only thing we need to do is find the dy dx here and check which one it matches. By the chain rule, that would be the derivative, and so A would be the correct answer here. That's the differential equation which has that function as a solution. You might have another type of problem where you're given a solution and you're asked to verify that it does solve this differential equation. So you can see that I have a double derivative here and y, so I need to find d squared y dx squared to check if that y is gonna solve that equation. So dy dx is gonna be negative 5 cosine x, and then, no, just positive 5 cosine x minus 2 sine x, and then d squared y dx squared is going to be negative 5 sine x minus 2 cosine x. So I'm going to take those and put the d squared y dx squared into this equation. I'm going to take this and put it in for that. I'm going to take this and put it in for this and check whether I end up with an identity or a contradiction. So negative 5 sine x minus 2 cosine x and I'm going to now add the y, plus 5 sine x plus 2 cosine x, and I'm checking, is it equal to 0? And I get, yeah, 0 is equal to 0. I get an identity. So this is true. This equation is solved. This differential equation right here is solved by this y. Okay. Next one, I want to show you that in this question, which says which of the following is the solution to the equation dy equals y dx, you're noticing that the dy and the dx have been separated. And we're going to do that more and more in this unit. You can put them back together or you can take them apart. You just treat them like fractions. So to put them back together here, I just divided both sides by dx. And it goes away here, and I get dy dx equals y. So then I have to go here and check which of these gives me a dy dx equals y. So dy dx is equal to e to the x, and that is exactly my y here. So this a works. For the second one, for b, dy dx would be e to the x. Y, though, is e to the x plus 2, so this does not work. C, dy dx is equal to 2e to the x, which is exactly the same as y, so this works. And let's check d. D is dy dx is equal to 2e to the 2x. That is not the same as e to the 2x, so that does not work, because the equation here says dy dx has to be exactly equal to y. That's my differential equation. So notice that the two that solved that were this guy here, e to the x, and 2e to the x. So we're noticing that those are the ones where the derivative is equal to the function itself. And we're going to come back to that. That's going to be a very important type of differential equation right here that we talk a lot about. Okay, let's come back here to 4. Which of the following is a solution to the differential equation? And now we have this differential equation, xy prime minus 3y equals 6. And we've been given these 4 possible solutions. So let's take them one at a time. For the first one, I have y is equal to x squared plus 2. So y prime, I'll work with the prime notation here, is 2x. So then I go back to this equation and I put it in and I see what happens. So x times y prime minus 3 times y, and I'm checking to see, do I get an identity or a contradiction? I get a contradiction here, right? It's definitely 2x squared minus 3x squared minus 6 is not equal to 6. So that means that this is not a solution. Okay, then let's do b. b is y is equal to 3x squared minus 2. So y prime is equal to 6x, and putting it back, x times 6x minus 3 times 3x squared minus 2, is it equal to 6, question mark? And I would say no, that also does not work. Checking number 3, or C, y is equal to 5x cubed. I believe it's 5x cubed minus 2. So then y prime is 15x squared, and then x times y prime minus 3 times y. We're checking, is it equal to 6? And I believe this one does work. 15x cubed minus 15x cubed plus 6 is equal to 6. So we get an identity, and it does work. The last one also, you're going to check like this and find out that it doesn't work. Okay, I had to fix some typos on this last problem, but we are asked to consider this differential equation and to determine which of the following equations here, A, B, C, or D, is a solution whose graph passes through the point -1, 3. So something we could do is check first which of these even passes through that point, let alone solving the differential equation, right? It has to do both. So we can first do the easy thing, which is check what happens when we put in -1 for x. So the first one, I get y would be equal to e to the -1 squared minus 1 plus 3. which I guess would be e to the 3. So that doesn't look like 3 to me, so that does not work. Let's do b. For b, if I put, these are all like y is equal to this, y is equal to this, y is equal to this. So if I say for b, y is equal to e to the, let's see, 1 minus 1 I would get plus 2. That's e to the 0 plus 2. Yeah, so that one definitely passes through this point, so it's in play. Let's do c. c is 3 times e to the 1 minus 1, which is 3 times e to the 0. So that one is also in play. And then d would be y is equal to 2 e to the positive 1 minus 1. So 2 plus 1, 3. So, okay, b, c, and d are in play. A we can eliminate because it doesn't even pass through that point. Now we look at the differential equation. Differential equation, let me just write it down here, is really dy dx is equal to y minus 1 times 2x plus 1. So now I just have to check b. So for b, dy dx is equal to e to the x squared plus x times 2x plus 1, and then the 2 goes away. So now I have to do y minus 1, so e to the x squared plus x plus 2 minus 1 times 2x plus 1, which is 2x plus 1. So I'm basically, here's my dy dx, that's this, right? So that's the left side here, and I'm checking is it equal to this for each equation. That's that, okay? So let's see, now I get, if I just simplify this, I get e to the x squared plus x plus 1 times 2x plus 1. So no, I don't think those two are equal, so I don't think b is going to solve it. Let's check c. So for c, the equation, the y equation is 3e to the x squared plus x. So the dy dx is 3e to the x squared plus x times 2x plus 1. And so now that's my dy dx, and I have to do y minus 1. So this is my left side of the differential equation, and I'm now doing y minus 1 times 2x plus 1, which is the right side. So I'll do it in blue again here. So y minus 1 times 2x plus 1. So we'll put the y in. Some of these take a little bit of doing. We'll put the y in, 3 e to the x squared plus x, y minus 1 times 2x plus 1. And now I'm comparing these two things, and they still don't look the same, right? So the red and the blue, so that doesn't work either. Let's hope the last one works. The last one, d, was y is equal to 2e to the x squared plus x plus 1. So my dy dx is going to be 2e to the x squared plus x times 2x plus 1. And I now, that's the red, that's my dy dx. And on the right, I had y minus 1. So that is going to be 2e to the x squared plus x plus 1 minus 1 times 2x plus 1. And I think this one, we are going to end up seeing that those two things, this red thing and this blue thing, look exactly the same, right? In other words, for this equation, it solves this differential equation where dy dx has to be equal to y minus 1 times 2x plus 1. Okay, so our takeaways are that the solution to a differential equation is a function. We need to be able to translate equations. You take words and, translate that into an equation. So try this one, pause the video, see if you get this. And I think that this would be dp dt. If we call the population p, then dp dt is equal to kp. There's another one of that natural growth equation that we're going to come back to soon. Then we have an integral or an antiderivative is a solution to a differential equation, right? It's a very simple differential equation. dy dx is equal to 5, right? You integrate, so get y is equal to 5x plus c. That is solving a differential equation. Now, solutions to differential equations may be general, like that 5x plus c that I just wrote, or particular. What do we do to verify that a function y solves a differential equation? Well, we just plug it in. We find all the necessary derivatives, and then we plug it in and see if we get an identity. If we get an identity, then it solves the differential equation. Okay, so I hope you enjoyed that, and we will talk again very soon.